In Table O, you're given a new chart that talks about symbols used in nuclear chem. So what you're going to notice, this people forget this is here, and on the Regents exam, you need to remember where that you can find.
Will they ask, like, what's the symbol?
Absolutely, they could say, what is the symbol of an alpha particle? But here's what they're likely to ask. They're likely to ask, what is the charge of an alpha particle? Now, how do you know the charge looking at this notation? The charge is always going to be written as the bottom number. The mass is the top number, charge is the bottom. So for an alpha particle, you would say positive 2. What is the charge of a beta particle? Very good. Beta, negative 1. Notice the charge and mass of a gamma particle. 0. They're massless and chargeless. The mass of a neutron is going to be 1. The charge of a neutron we know is 0 because it's neutral. So that's what they're most likely to ask. They'll say, what is the charge? Or they might say, what is the mass? And you need to know where to look to find that. All right, so table O.
It goes mass, then charge.
Always mass in the top. Now, if you forget that, Hannah, think about how we write isotopes, and it's the same way. Yeah, absolutely. You can look at a periodic square and find that same notation. The only difference is this stands for the atomic number. It doesn't specifically stand for charge on the atomic square, but the mass is always given on the top, and then the atomic number. Here in this notation, it's the mass and then the charge. All right, so mass always on the top. What's that? Yeah, exactly. So you'd say positive 2, and like down here for a proton, positive 1. Okay? Notice that almost all of these have 2 symbols that you can work with. You can work with, the He, which is basically called the nucleus of a helium atom, or you can work with an alpha particle. Good job. Okay, so for our worksheet here, we are down to number 12. List the symbols in number 11 in order of increasing penetrating power. Now, you might have had to look this one up to Google it. Basically,
Yeah, it's on a quiz.
was
What
it?
is the highest?
Oh, yeah, you're right. This is basically asking you which type of radiation is the most dangerous. Alpha, beta, then gamma. For those of you who were in lab yesterday, we went out and we just stuck our heads into the dental bus.
That's
really.
how I knew number 13.
Yeah, and we talked to them. I was going to say, I talked to them specifically. I noticed that they had the 3 chairs quite close together for working on patients, closer than what would be in a normal office. And I said, how do you guys kind of prevent, your cells from getting radiation exposure? Because when you get an X-ray, and an X-ray is using gamma radiation, so it's not like, okay, one X-ray is going to cause mutations in your body, but you don't want to be exposed to it day in, day out. And they had this cool little curtain that had a thin layer of lead in it. I don't know if you heard them say that, but they just pull it around, and that thin layer of lead is really good. Lead is very dense, and it works well at stopping. That's exactly right. So when you take you should have it be covered in vests, and those are heavy.
Yeah, they are.
I mean, when they stick on, it's like, man, get this thing off me.
How is I don't know, is lead malleable enough?
Lead is extremely malleable.
Is that why it's so flexible?
Yes, it is. Lead is.
I wondered when they put when I got
Yep.
X-ray.
It basically folds around you.
It just bends
Lead,
your body.
and that's actually why it's also used in bullets. They want lead to be able to basically expand on impact, but in a lead vest, such as an X-ray, you're right. It just literally curves around your chest. So when they stick that thing on you, it wraps around you. Lead is very soft, very.
Lead pipes. Those are
Yeah, you're
those
right.
have to be alloys. They can't just be one done. They can't be just lead. They'd be so soft.
No, I think you're right, Caleb. There must be an additive to make that slightly more either rigid or flexible. This is crazy because typically lead pipes are not used anymore because they don't want the lead leaching into water. So I don't know if I've actually worked with lead pipes, but I think it would be an alloy.
When they redid our barn, that's all they had was lead pipes. And
Yep.
now they're laying outside my garage right now, just sitting there.
You might be able to scrap those.
I didn't
I'm
know
not
if you could. I
sure.
don't know if they accept.
I don't know
lead.
either. That's a really good question. Number 14. When two protons and two neutrons combine to form helium, the mass of the helium is slightly less than the combined mass of the protons. Explain this term called mass defect. Did anyone get it? This is Einstein's equation. It's a very famous equation. You see Einstein saying E is equal to mc squared. The E stands for energy. M is mass. C is the speed of light squared. Here's what it means. When you have two atoms come together, and form a bigger atom, some small amount of mass gets converted into energy. Einstein said that mass can be converted to energy, and energy can be converted to mass. At what atomic number do isotopes become radioactive? Anything above
83.
83. If you notice, 83 is what element? Bi. Some waterfowl hunters knows what Bi is. Really expensive bullets. It's called bismuth, and it's more dense than lead, but it's very expensive. Anything above that is radioactive, but this is the first. So anything above 83 becomes radioactive. Madison, you have a question?
I looked that question up and it said that like a hydrogen isotope with atomic number of 3 is radioactive.
Very good question. Yeah. So you can have isotopes of elements below 83 that are radioactive. So there's a lot of radioactive isotopes that are less than the number of 83, but there are a lot of ones that are also stable. All right. So each element has multiple isotopes, but almost all of the isotopes of any element above 83 are radioactive, whereas some of the isotopes below 83 may not be. Jess?
Wait, I have a question. When we get to 16, I guess.
Okay.
What, like, you just talked about these bullets being
Bismuth?
more dense than lead.
Mhm.
But is it, like, as poisonous as lead?
No, that's the beauty of it. You can use
That's
it.
like, you have to use, like,
That's why they're
brass,
super
like-
expensive. Is that they carry the energy of lead well, but they're not. They don't have the same toxicity as lead, so you can. But they're really expensive.
Yeah, I just wondered.
So I just use steel, but then it limits your range. Okay, 16. Jess.
I thought protons and electrons were the same. No, I thought protons and neutrons were
In the same what?
the same number. Yeah, but they're the same.
Protons and electrons are always the same atomic number if you're not dealing with an ion. So here's the deal. For the first two, you'll notice the protons and electrons are absolutely equal. But now that rule breaks down when you have an ion that becomes charged. So, chlorine has 18 electrons because it has gained 1. Cassie, what are you doing? Good. Just checking. I saw the fingers flying.
It's called scrolling.
I'm okay with that. Now, what you'll notice is chlorine has 17 protons. The atomic number of chlorine is 17. But when you become Cl negative, you gain an extra electron. Now, on Mg, Mg is a metal, all right? So it's going to lose 2 electrons, and that's why you'll see that the electrons are 2 less than the number of protons.
What about B? I thought protons and neutrons were the same. No,
Protons and electrons are the same. Now, let's take a look at the atomic square. The atomic square for sodium is you have an atomic number of 11 and an atomic mass of 23. To find the number of neutrons, you subtract them. That's why you get 12. Okay, so that's why they're not the same for the protons and neutrons. The protons and electrons for an atom have to be identical. Getting it? All right, so if I said to you, if I give you let's do one more of these just to make sure everyone's getting it. Please tell me the protons, electrons, and neutrons for calcium, but then tell me the protons, neutrons, and electrons for the calcium ion. All right, and that is atomic number of 20. Atomic number of 20.
By the way, Mr. I have things in the grade book without any. Yeah, me too.
You have things that are out,
Yeah, that I have done.
okay?
Finding-
Why not during lab we take a look at those?
Holy book.
I'll try to add them. Or Monday, it's fine.
It's out of-
So for calcium, how many protons, Madison? Good. Electrons and neutrons. You got it. Now for the calcium ion, what changes? So the number of electrons will go to 18
Why?
Yeah, you lose that.
because you've lost 2 of them. You've lost 2 when you've turned into the calcium plus 2 ion.
So the two stay the same as the electrons always change.
The electrons is the only thing that changed between an ion to an atom. You will never have protons or neutrons changing when you go from an atom to an ion. Now let's try one with nonmetals. Let's look at fluorine and fluorine -1. Go ahead and tell me the protons and electrons, neutrons for both of these. You sure would. Protons would be, nope, 9. Electrons would be 9. Neutrons would
I was
be
looking at nitrogen.
10. And then for the fluorine -1, protons, 9, 10, 10. Yep. Got it? Good. Good, good, good. Okay.
Yes.
It's like 8.
Yes, we are.
Who cares?
Wait, is there anything green though?
Cares who?
Tests are in the grade book.
My ears won't pop.
Yes.
Let me think. Did I put them in? No, I have not put them in, but I've got them.
Just put them in right now.
I've got them recorded. So stop me at 9:30, and I will pass out tests. All right, and then I'll give you a chance to kind of look at them and bring them back with questions. Okay, so under nuclear chem here, we're going to start talking about nuclear reactions, but we have to get through this little part of notes
Wait, make
here.
sure you record for Zoe.
I'm recording.
Okay.
Thank you.
Yeah.
Yep, I've been recording. So the stability of a nucleus is determined by the neutron to proton ratio. So we've just been kind of doing this when we've been just kind of messing around there with some practice things. But for oxygen, oxygen obviously has an atomic number of 6 and it has an atomic mass of 16. So how would I find the number of neutrons to the number of protons? Oh, and I'm wrong here. I said obviously 6 and it's obviously 8. Carbon is 6. Wasn't so obvious. So neutrons would be what? Yeah, 8, and protons would be 8, so 1 to 1 would be our neutron to proton ratio. Below the atomic number of 20, the ratio 1 to 1 gives the greatest stability, okay, or the ratio that gives the greatest stability is 1 to 1. One more time, determine the neutron to proton ratio of Rn. Now, Rn, you've got to find it on your periodic table. Tell me the number of neutrons, somebody. It's the atomic number of 86. So look at 86. What is our number of neutrons? The atomic so 222 minus 86 and you get 136.
136.
So you have 136 neutrons, and then the atomic number gives us the number of protons at 86. So when you take that ratio, you end up getting the ratio of 1.5. So above the atomic number of 20, the ratio of stability is about 1.5 neutrons to every 1 proton. So you need more neutrons compared to the number of protons. All the elements above the atomic number of 83 are radioactive due to their neutron to proton ratio falling outside what is called the band of stability. And because they fall outside of the band of stability, they undergo radioactive decay in order to gain stability.
says graph gain stability.
Okay, I'm gonna skip this part and jump down to
Just kidding,
And
Hannah.
Samuel H. Jackson.
Who's that sound?
Intro to Radioactive Decay. Quick review. Isotopes are atoms of the same element. What do they have the same number of?
Protons.
Good job. Protons and electrons, but different number of
Neutrons.
neutrons. Good.
Are we gonna graph the band of stability?
Nope, we're not.
We're not.
We had said that carbon 14-6 and carbon 12-6 are two different isotopes of the same atom. Unstable isotopes are called radioisotopes. You getting this, Cassie?
Mhm.
Unstable isotopes are called radioisotopes. And radioactivity is defined as the process in which materials give off radiation in the form, or energy, sorry, in the form of radiation. They give off energy in the form of radiation. Radioactive decay is the result of an unstable nucleus losing energy by emitting radiation to form stable isotopes of a different atom. And what we're going to focus on today is types of radiation in terms of that beta, alpha, and gamma. Radioactive decay therefore involves nuclear reactions, not chemical reactions, because we are not dealing with transfers of electrons, but we're changing the nucleus. Okay, types of radiation. The first one we're going to talk about is an alpha particle. So an alpha particle is actually simply the nucleus of a helium atom. If you just talk about the nucleus of a helium atom without its electrons, right, then you're dealing with an alpha particle. And an alpha particle is made up of 2 protons and 2 neutrons.
Oh my gosh, I'm so
Alpha particles are produced when one nucleus breaks into 2 smaller nuclei. Now, we have just checked table O, and table O gives the notation. There are 2 of them for alpha particles. If you remember, the first one is just represented by the nucleus of a helium atom, so He42. You can also, however, write this
Did you just say? No.
nucleus of a helium atom.
No. I feel like you said it.
What a nucleus on a fish.
What would I say? Did
I
I
don't know. I
reverse it?
totally like,
I might have
around.
reversed it. I don't know.
That fly.
Now, when we do a nuclear equation, you have to remember something really important. Mass and mass and charge are conserved. And because mass and charge are conserved, you can figure out how to write nuclear equations by balancing mass and charge. As an example, if you have uranium 238 and 92, and I tell you that this undergoes alpha emission, which means it gives off an alpha particle, you can figure out the other product. Here's how it works. You got it. So Hannah actually just figured this out. She's looking here and she's saying, I've got 2 on the right. I've got to get back to 92. And Hannah, what you just did is the most important thing. You always start by finding the atomic number. Because once you know the number, then you can go to the reference table and find the symbol. And it is absolutely, Claudia, thorium. Do not look at the reference table to find the mass of thorium, because it may not be what the mass is that we're looking for, because thorium has different what? Isotopes. So what you do is what you had already done, Hannah. Ask yourself, what can you add to 4 to get back to 238? And the answer is 234.
So you just change it to whatever that was.
That's right. You basically conserve mass and conserve energy on the left and right hand side of the arrow. The clue for this, when you have alpha decay, is that the atomic number will go down by 2 and the atomic mass will go down by 4 as you go from the left-hand reactant to the right-hand product. Alpha particles have low energy. They are stopped by your skin. You do not end up getting cancer from alpha particles because they are low enough energy, they don't harm you. Number 2, these guys are called beta particles. Beta particles are formed by the decomposition of a neutron as it turns into a proton. That proton remains in the nucleus, but an electron is released along with something that you really don't need to know much about, but it's called a neutrino. But it's the key that the electron gets released. These fast-moving electrons are given the name beta particles. Again, there are 2 symbols for them. You can have the symbol 0e negative 1 or the symbol 0b beta negative 1. Okay, let's see if you can do this now. Let's say that I have carbon 14-6 and I tell you it undergoes beta emission. Can you figure out the other product? Right there. It would have to be 14-7. You know that you have to add something to negative 1 to get to 6, so that's where the 7 comes from. Something added to 0 to get to 14. How do I figure out the symbol? The 7. Go to the reference table, find your element. You got it. That's exactly right.
It is
Correct. Because you've got to add them to do that. Let me do the last one here. Gamma radiation is radiation of high energy. A gamma particle is actually a particle of light called a photon. And it's produced in the radioactive decay chain. The symbol we know is 0, 0. Yes, it is. Thank you, Claudia. If you have gamma radiation, it will look like this. Absolutely. This undergoes alpha and gamma radiation. Okay, so that symbol looks something like that. So that's how you would see it in the reaction. These guys here are very dangerous. All right, those guys there are very dangerous. A beta particle, by the way, this is moderately dangerous. Called moderate energy. So, somewhat dangerous. You don't want to be exposed to them all the time. But you definitely want to avoid gamma radiation.
Weird.
Close to the end.
So you do the.
You won't be asked to figure that one out. But if you are, sometimes they will ask you them, and neither the mass nor the charge will change. So you're not really going to be asked much about that one. It does. Yep. But you're not going to be asked one like that where it gives you 2 forms of decay and then asks you to find the third. That would be very uncommon. There's one more that I want to add because it's very similar to beta decay. It's called positron emission. A positron is identical to a beta particle, but it has a charge of +1 rather than -1. It is not a proton. A proton has a mass of +1. A beta particle still has a mass of 0, but it has a charge of +1. If you undergo beta decay, it looks something like this. If you have boron 8,5 and you emit a beta particle, that is, sorry, if you emit a positron, you end up getting 0 positron symbol plus 1. What would be your other product with positron emission? It would have to be 8, 4. I totally agree with the 8, 4. And your symbol that has the 4 is beryllium.
So it always is like the opposite. So if it's negative, you're gonna.
I just always ask myself, what can I add to this number to get back to here? So I need to add 4 to 1 to get to 5, 8 to 0 to get to 8. But on this side, because that was a negative, I have to add a 7 to negative 1 to get to 6. Okay? All right. Good job with that. Let me hand out tests.
Hey. Yeah.